The sound wasn't loud at first. It was a low, almost patient hum moving through steel. A vibration you could feel in the railing before you could hear it in the air. On the morning of November 7, 1940, drivers crossing the Tacoma Narrows Bridge in Tacoma noticed something strange. The roadway beneath their tires wasn't just shifting, it was rising and falling in long, rolling waves, like the surface of dark water. The bridge had only been open a few months. It was a brand new suspension bridge, part of a major civil engineering push to connect communities across Puget Sound. The wind that day wasn't extreme by Pacific Northwest standards, roughly 40 miles per hour. The kind of steady coastal wind the structure was designed to survive without drama. And yet, the deck was moving. There had been signs. Even before opening, workers nicknamed it Galloping Gertie. The slender roadway would ripple in moderate wind, a vertical undulation engineers initially described as normal flexibility. Flexibility was modern. Flexibility meant efficiency. Long-span suspension bridges were supposed to move. That was part of the design philosophy of the era. Steel towers, massive main cables, a stiffening girder system, all working together to distribute loads and handle wind forces through controlled deflection. But controlled was the key word. The Washington State Toll Bridge Authority had approved a design that was elegant and cost-conscious. The consulting engineer, Leon Moiseeff, was respected. He had worked on the George Washington Bridge. His theory leaned on deflection rather than brute stiffness. Let the wind pass through. Let the structure move with it. But here's the detail that keeps resurfacing in engineering retrospectives. The stiffening girder was unusually shallow. Instead of a deep open truss that allowed air to flow through the deck, the bridge used solid plate girders along the sides. Clean lines, less steel, lower cost. The board overseeing the project had chosen a cheaper steel supplier to keep the budget under control during the late 1930s, when public works funding was tight and every dollar was scrutinized. On paper, the material met specifications. It passed inspection stamps. No one could point to a single failed test coupon and say, that's where it went wrong. Still, the deck moved more than expected from the beginning. Drivers reported the sensation weeks after opening. Newspapers covered the strange oscillations with a mix of fascination and civic pride. This was a bold, modern structure, a marvel of civil engineering. Motion wasn't automatically a flaw. Engineers installed hydraulic dampers in an attempt to calm the vertical movement. They added cable tie-downs. They brought in wind experts, but the fixes were reactive, temporary. None addressed the deeper aerodynamic question that hadn't yet been fully understood. What happens when wind doesn't just push on a bridge, but starts to synchronize with it? By late October, the motion had changed character. It wasn't just vertical bouncing anymore. It began to twist. On November 7th, traffic was light. A few cars crossed. Wind moved steadily through the Tacoma Narrows. Witnesses later described the bridge deck rotating several feet from side to side, one edge up while the other dropped. Torsional oscillation. Not random shaking, but rhythmic rotation. Engineers would later call it a resonance disaster, a self-exciting aerodynamic instability, where the structure's natural frequency locked into the wind's energy. At the time, people on the bridge just saw the roadway tilt. This wasn't a hurricane. It wasn't an earthquake. It was steady wind interacting with a design that may have been too slender. Material fatigue wasn't the initial trigger, but the repeated stress cycles didn't help. Around 10:30 a.m., the oscillations intensified. The bridge didn't snap instantly. The structure continued to twist, each cycle feeding the next. And then, in a sequence that lasted minutes, sections of the roadway began to tear loose. It would become one of the most famous structural failures in American history. But in that moment, standing on the shoreline, watching steel fold into the Narrows, the question wasn't about theory. How did a bridge designed by top engineers begin to breathe itself apart in ordinary wind? Because what failed that morning wasn't just a span of steel. It was an assumption about how far you could push efficiency before physics pushed back. In the weeks after the collapse, the footage of the twisting deck spread far beyond Washington State. But inside conference rooms and state offices, the conversation was less cinematic. The official investigation didn't begin with a villain. It began with math. On paper, it worked. But the Tacoma Narrows Bridge introduced something the calculations didn't fully capture: aerodynamic lift, interacting with torsional flexibility. Each rotation fed more energy into the next. The solid plate girders played a role. Air hit it, separated, and reattached in unstable patterns. What engineers would later define clearly as aeroelastic flutter was, in 1940, not yet fully understood in bridge design. Early reports examined the steel quality. The supplier had met the specified grade. Test results showed no obvious metallurgical defect. No brittle fracture triggered the initial motion. But cost-cutting had influenced decisions long before the first piece of steel arrived on site. The board overseeing the project had prioritized a lighter, cheaper design. A narrower deck, shallower stiffening girders, fewer materials overall. The philosophy wasn't reckless, it was efficient, but it reduced the margin for unexpected behavior. Material fatigue wasn't the primary cause of collapse, but the months of oscillation before failure had stressed joints and connections. Bolts loosened. Expansion joints worked harder than intended. Maintenance crews had attempted adjustments. Hydraulic dampers were installed, but proved ineffective once torsional motion began. Cable tie-downs snapped under repeated stress. There's a detail that often gets overlooked. The bridge didn't collapse under peak wind speed. It collapsed under a speed it should have survived comfortably. That fact shifted the investigation away from extreme weather and toward design assumptions. Wind tunnel testing was not standard practice for bridge decks at the time. Engineers relied on static calculations and experience from previous projects like the Golden Gate Bridge and the George Washington Bridge. But those structures had deeper, more open truss systems. They behaved differently under wind. Tacoma Narrows was thinner, smoother, more streamlined. The state appointed panels of engineers and academics to study what had happened. Early debates centered on whether the issue was resonance from vortex shedding, a rhythmic pattern of air swirling behind the deck, or a more complex flutter phenomenon involving torsion. Over time, research confirmed it was the latter. The bridge had entered a self-exciting oscillation mode. Once that mode started, damping systems were insufficient to stop it. The collapse forced the engineering community to confront something uncomfortable. Advanced mathematics had outpaced empirical wind testing. Designers trusted theory that wasn't yet complete. Meanwhile, along the shoreline of the Tacoma Narrows, the aftermath was quieter than the headlines suggested. The towers remained standing. Cables draped across the water. Sections of the original deck sank into the channel below. Over time, twisted steel fragments were salvaged and, in some cases, used as riprap along the riverbank. Large rocks and debris placed to prevent erosion. Pieces of a failed experiment embedded into the landscape as erosion control. It's a strange legacy. The remains of a resonance disaster turned into shoreline protection. But the deeper impact wasn't visible from the water. Civil engineering changed. Wind tunnel testing became standard for major bridge projects. Aerodynamic stability was no longer assumed, it was measured. Future suspension bridges incorporated open truss designs or perforated decks to reduce lift forces. Engineers began treating long-span bridges less like static structures and more like dynamic systems, interacting continuously with wind. Still, even as textbooks updated and research advanced, a question lingered in professional circles. If the bridge had shown warning signs from the beginning, the vertical undulations, the nickname, the dampers that didn't quite work, why wasn't it closed earlier for a fundamental redesign? Why were temporary fixes considered enough? That question doesn't have a single answer. It touches budgets, public pressure, confidence in respected engineers, a belief that the motion was dramatic but not dangerous. No one expected ordinary wind to become destructive through amplification alone. And yet, that's exactly what happened. The Tacoma Narrows collapse is often taught as a clean lesson in resonance and aeroelastic flutter. But in reality, it was a chain of small, reasonable decisions. A lighter deck to save money, solid plate girders for efficiency, confidence in deflection theory, limited wind modeling, incremental fixes instead of structural overhaul. Individually, none of those choices looked catastrophic. Together, they created a bridge that could breathe, and once it started breathing in rhythm with the wind, there was no mechanism strong enough to quiet it. What happened next politically, financially, and structurally, would determine whether Tacoma Narrows became a permanent warning or a temporary embarrassment, and the answer would reshape suspension bridge design for the rest of the century. In the months after the collapse, the twisted steel in the water became less of a spectacle and more of a liability. Insurance claims had to be processed, bonds had to be addressed. The Washington State Toll Bridge Authority faced hard questions from legislators and the public. This wasn't just a failed structure, it was a failed investment during an era when public works projects were meant to symbolize stability and progress. Financially, the loss ran into millions of dollars, a staggering sum for 1940. But the greater cost was reputational. Civil engineering had been riding high through the early 20th century. Massive dams, skyscrapers, and record-breaking spans had reinforced the idea that modern engineering could outthink nature. Tacoma Narrows forced a pause in that narrative. Investigators released findings that were technical, careful, and restrained. They didn't accuse a single engineer of gross negligence. They didn't claim the steel was defective in some dramatic way. Instead, they described a design that lacked sufficient aerodynamic stability. The solid plate girders increased susceptibility to torsional flutter. The narrow, shallow deck reduced structural damping. Wind tunnel testing had not been performed prior to construction. These weren't criminal acts, they were gaps in understanding. But outside technical circles, the explanation felt unsatisfying. How could a bridge collapse in steady wind without someone being clearly at fault? The board's earlier decision to prioritize cost efficiency came back into focus. Meeting minutes showed pressure to keep the project within budget. The design's reduced steel usage was celebrated as innovation. Choosing a cheaper steel supplier wasn't illegal or unusual. The material met required specifications. Yet in hindsight, every effort to trim weight and expense narrowed the margin between acceptable motion and catastrophic instability. The bridge had been engineered to the standards of its time. The problem was that the standards were incomplete. What changed next wasn't a single law or a dramatic public trial. It was a shift in process. Wind tunnel laboratories expanded. Universities began constructing scale models of bridge decks to study airflow behavior under controlled conditions. The concept of dynamic load analysis gained new urgency. Engineers no longer relied solely on static load calculations and safety factors. They began modeling vibration modes, torsional stiffness, and aerodynamic lift interactions as standard practice. The replacement span of the Tacoma Narrows Bridge looked different. It was heavier and more conservative. Some critics said it was less elegant, but it didn't gallop. The original towers that survived the collapse were incorporated into the new design. They stood as quiet reminders of what had failed. Beneath the water, pieces of the 1940 bridge remained. Sections of steel were removed over time, while other fragments settled into the riverbed. Some recovered pieces were repurposed along the shoreline as riprap. It's almost symbolic. A failed bridge now reinforcing the edge of the same waterway that once amplified its weakness. In engineering classrooms, the footage became a staple. Students learned terms like vortex shedding and aeroelastic flutter through Tacoma Narrows. Professors emphasized something subtler: systemic optimism. The collapse didn't end suspension bridge construction, it refined it. The post-war boom would produce even longer spans. Built with aerodynamic decks shaped by wind tunnel data, these structures incorporated lessons from 1940. Yet the deeper lesson wasn't just about wind, it was about margins. When boards push for lower cost and designers celebrate material efficiency, the system drifts closer to its limits. This happens not because anyone intends failure, but because success creates confidence and narrows caution. The Tacoma Narrows Bridge didn't collapse because steel is weak. It collapsed because a complex dynamic system was simplified too much. Wind was treated as a static load instead of an active partner. Flexibility was embraced without fully understanding how it could synchronize with energy in the environment. The moment the bridge began to twist that morning, there was no emergency switch. No rapid shutdown protocol for wind. Only physics continuing its cycle until connections tore apart. Today, drivers cross a stable span without noticing anything unusual. The hum of traffic blends with the wind. The deck feels firm. Engineers quietly monitor vibration data and structural health metrics in real time. That level of surveillance is part of the legacy too. But along the shoreline, pieces of 1940 remain embedded in rock and sediment. Steel, once meant to carry cars, now holds back erosion. A bridge that breathed itself apart. And a profession that had to admit it didn't yet understand everything about the air moving around its own creations. The collapse cost millions and pride. It forced a generation of civil engineers to rethink assumptions about material fatigue, resonance, and aerodynamic design, and it left behind a question that still echoes in modern boardrooms and design reviews. When budgets tighten and innovation promises efficiency, how thin can you go before the structure starts to breathe again? If you stand near the Tacoma Narrows today, the wind doesn't sound dramatic. It moves through the water the way it always has, steady and indifferent. Cars cross the modern span without slowing. Most drivers don't know they're traveling above the site of one of the most studied structural failures in history. There's no vibration under their tires, no rolling wave beneath the asphalt, just a bridge doing what it's supposed to do. That quiet performance is the real legacy of November 7th, 1940. The original Tacoma Narrows Bridge collapsed because wind found a rhythm the engineers hadn't measured. The replacement span exists because engineers decided never again to guess at that rhythm. In the decades that followed, wind tunnel testing became embedded in civil engineering practice. Scale models of proposed bridges were subjected to controlled airflow long before steel was ordered. Designers studied torsional stiffness as carefully as tensile strength. Aerodynamic deck profiles were refined to reduce lift and prevent vortex lock-in. The language of bridge design shifted from purely static load factors to dynamic systems analysis. That shift extended beyond bridges. High-rise buildings, long-span roofs, offshore platforms all began incorporating more rigorous vibration and resonance modeling. The concept of structural health monitoring evolved. Sensors now track movement in real time, feeding data to control rooms that can detect abnormal oscillations long before they become visible. Tacoma Narrows wasn't just a collapse, it was a correction. And yet, when engineers revisit the archival footage, what stands out isn't just the twisting deck. It's how long the motion was visible before failure. The bridge didn't fail in an instant. It warned, it flexed, it oscillated for months before the final breakdown. The system communicated stress, but the interpretation lagged. That's the part that still resonates in modern project reviews, because the board that approved the lighter, cheaper design didn't intend to build a failure. The consulting engineer didn't set out to test aerodynamic limits recklessly. The steel supplier delivered material that met specification. Each participant operated within the accepted framework of the time. But frameworks evolve. Cost efficiency narrowed the structural margins. A shallow, stiffening girder reduced weight, but also reduced torsional resistance. Solid plate girders streamlined the profile but trapped unstable airflow. The absence of wind tunnel testing wasn't negligence in 1940, it was standard practice. The disaster exposed that standard as incomplete. That's why the story persists, not as a scandal, but as a system-level miscalculation. Even today, large infrastructure projects face similar tensions. Boards weigh budgets against resilience. Designers balance aesthetics against redundancy. Contractors compete on material pricing. And engineers rely on models that are only as complete as current knowledge allows. The Tacoma Narrows collapse reminds the industry that nature doesn't care about budgets or elegance. Wind doesn't negotiate with spreadsheets. It interacts with geometry, stiffness, and mass in ways that can amplify small misjudgments into structural instability. Along the riverbank, some of the twisted fragments from the original span remain embedded as riprap. Steel, once suspended 200 feet above water, now sitting quietly at the shoreline, holding back erosion. The pieces don't look dramatic anymore. They look like ordinary rocks and debris. But they're not ordinary. They are the physical evidence of a bridge that began to breathe in steady wind. Not because of sabotage, not because of extreme weather, but because a system underestimated dynamic interaction. A resonance disaster that cost millions and reshaped civil engineering worldwide. If you replay the film, you can see the moment the deck shifts from vertical waves to torsional rotation. That's the pivot. The instant when flexibility crossed into instability. The point where efficiency met physics and physics won. And that low hum at the beginning, The vibration in the railing, the subtle motion under tires, that was the first signal. The bridge speaking in the only language it had, movement. In hindsight, it feels inevitable, but inevitability is just clarity that comes too late. Today's bridges are stronger not because engineers are braver, but because they listen differently. They test more. They measure airflow. They model vibration. They build in margins that account for what they can't see. The wind still moves through the Tacoma Narrows. It always will. The difference is that now, the bridge moves with it and stops there.